Welcome to SRA 221. In this video, we will continue our discussion on classic cryptography. So far, we have used two techniques used in cryptography, which are substitution and permutation. We have seen that substitution suffers from many vulnerabilities due to the ability of the attacker possibly reconstructing the substitution key. The same can actually happen with transposition. The attacker is able to reconstruct the plain text by understanding how the sub-blocks are organized. So we know that substitution and permutation are weak. DES would be a modern and actual commonly used algorithm that is strong enough to overcome a possible basic cryptanalysis technique based on frequency of usage of certain words or letters. In order to have a secure cryptosystem, ideally what we are looking for is something solid, a mathematical proof or some guarantee that there is no visible attack in the system. Now, this concept is very hard to prove, and in fact, in modern cryptography, we try to lower this requirement to something more concrete. So typically, a cryptosystem is defined as secure if the best known attack on that cryptosystem requires as much work as an exhaustive key search. We will now take a look at one time pad, which is a provably secure cipher. No other cipher that we discuss will be classified as provably secure. Here is an example of a provable secure cipher. This is the only one today, and it is the only one which can be mathematically proved, essentially stating that there is no other attack other than the key exhaustive search for breaking this algorithm. Now consider this example has a plain text and a ciphertext. In this plain text, we use Hail Hitler. Place yourself in the context of World War II and consider that we have a spy named Alice. Alice needs to send a message, so we have the plain text here and we have a key. Digital encoding is shown here, and assume that we are only using a very small alphabet. E is equal to 000, H is equal to 001, and so forth. These are the only letters in our alphabet. So how are these computed? Are these simple exclusive OR or XOR? Interestingly enough, here you can see is that if you were to do the reverse approach here, you could reconstruct the message quickly. The original message, Hail Hitler, is obtained from the ciphertext plus the very same key that we use for encryption. So now suppose that Alice is captured and the double agent Bob uses a different key. The key that is reported here is used as a one-time pad, which actually changes the message completely, as it would actually read as Kill Hitler instead of Hail Hitler. So you can see here that the semantics changes here completely. Unfortunately, because the key is randomly generated, there is no way to bind the original plaintext with the ciphertext. So Alice has no way of proving that this is not the key that she used. Here you can see that you would obtain a completely different plaintext if you used a different key with the same ciphertext. The key here has a different encoding and will produce a different result, just as we discussed in the previous slide. What we discussed is a provably secure application. When used correctly, the key is never used more than once. The advantage is that the ciphertext provides no information about the plaintext, and all plaintexts are equally likely, which is a wonderful global property of this algorithm. Additionally, the pad must be random and it must be used only once. The pad is only known by the sender and the receiver, and the pad is the same size as the message. Significantly, you can see that there is no assurance of message integrity in one-time pad. Now that we have seen how encryption techniques work, we need to evaluate how they are used in the real world. In theory, this is a cryptosystem that we like to see. You want to ensure that there is a shared secret key between host A and host B. The two of them have some plain text, then encrypted using their shared key. They then obtain some ciphertext, which is a message that is sent over an insecure channel, which is then decrypted using the decryption algorithm for the algorithm being used. So you may be wondering, how do we actually get the key to the receiver? There are a couple of options here, with the most obvious being to mail it. Additionally, you could drive to the recipient, but if you do that, why not just deliver the message there? You could also hide it in a JPEG image, or you could send the key over a secure channel. You can see here that there is a list of insecure and secure channels just to give you an idea. And an insecure channel is the internet, but also wireless connections, Ethernet, and so forth.